In this module, we will consider that the free wave solutions from the previous module are actually coupled to diabatic heating in the tropics. We'll then examine the vertical structure typically seen in these equatorial waves coupled to diabatic heating. The actual pattern of OLR in equatorial waves projects well onto Matsuno's solutions for equatorial waves, which are plotted in these two panels by lines that represent different phase speeds for some given value of n. The waves with convection that is asymmetric about the equator include the even-numbered inertia gravity wave, the n equals 0 eastward inertia gravity wave, and the mixed Rossby gravity wave. The waves that contain convection that are symmetric about the equator include the odd-numbered westward inertia gravity waves, the equatorial Rossby wave, and the Kelvin wave. The colors indicate pairs of frequencies and wave numbers at which variability in observed tropical OLR occurs, mostly, between 15 north and 15 south. So for example, we can see the westward inertia gravity wave at n equals 1, but we don't really see any OLR activity in the eastward inertia gravity wave at n equals 1. However, the observed phase speeds are generally less than what would be predicted by dry equatorial wave theory, meaning the theory without considering the effects of moisture and diabatic heating on the circulation, which must be considered. In other words, when we consider that these waves have vertical structure and do not actually occur in a single layer shallow fluid, the thermodynamic equation must be considered. It links the anomalous flow to the diabatic heating through mass continuity. In the previous module, we defined a Rossby radius, which describes the off-equatorial distance at which an equatorial gravity wave begins to feel the effects of rotational flow. Here, it is shown as dimensional with units of meters. This distance depends on a quantity we will call the equivalent depth. This quantity is related to the stability of the atmosphere and the vertical wavelength of the diabatic forcing, or just the vertical wavelength of the wave structure. Equivalent depth corresponds to the depth that a shallow water gravity wave would need to give a phase speed of root GH that matches the observed phase speed in nature. And so here's the root GH in this table up here. We'll get to in a moment. It is only a theoretical depth in our shallow water model of equatorial waves and does not correspond to any actual physical depth in nature. We can readily examine how convective coupling might occur when heating is first baroclinic, which you may recall means that the heating peaks in the middle troposphere, is the same sign throughout the troposphere, and goes to the ground, or goes to 0 at the ground and the tropopause. First, we'll look at equivalent depth in the context of just dry waves that have first baroclinic structures as well, but with no heating. For a typical environmental lapse rate of 7 degrees C per kilometer, and a tropospheric depth of about 14 kilometers, corresponding to a vertical wavelength of 28 kilometers, the equivalent depth would be about 200 meters, which is denoted by the red arrow and this row in the table. A 200 meter equivalent depth corresponds to a phase speed of about 45 meters per second if you plug the 200 meters into this root GH. We can combine our horizontal momentum equations, the mass continuity equation, and the thermodynamic equation to get an expression for how geopotential changes as a function of divergence in the wave. The vertical gradient of geopotential, or the thickness, is proportional to the temperature, and so no diabatic heating is included in the thermodynamic equations either, as denoted by this 0. The resulting equation in the red box looks essentially the same as the mass continuity equation written in terms of geopotential, except that the equivalent depth is now used, and the phase speed is root g times equivalent depth instead of just root gh. Here, we have assumed that geopotential has a first baroclinic vertical structure. The solution we just outlined was for dry equatorial waves with an assumed vertical structure. Dry here means that the waves are uncoupled to latent heating. These are also known as free waves. Some dry Kelvin waves, for an example, are observed in nature. However, the power in the Kelvin wave, part of the wave number frequency diagram, is concentrated along lines of equivalent depth that correspond to slower moving waves than the 45 to 50 meter per second waves of the dry mode. For example, the observed propagation of equatorial Kelvin, or eastward moving gravity, waves correspond to an equivalent depth of about 25 meters. We can try to emulate this depth using our existing mathematical framework by simply adding diabatic heating, or cooling, Q, to the thermodynamic equation. We now have a set of equations with no analytical solution, however. One way of simplifying the equation system is to assume that the diabatic heating varies linearly with the vertical motion, in this right here, or Q related to W times N squared. In this way, we can express Q in terms of omega or W. This is basically another way of saying that the atmosphere and convection are in quasi-equilibrium, which is a topic for a more advanced course in tropical meteorology than this one at NPS. In this case, the so-called effective static stability is reduced, such that the value of n in the expression for equivalent depth is reduced. For this, the phase speed of the coupled wave is reduced proportional to the offset between the adiabatic cooling and the condensational heating associated with the upward motion. The same is true for opposite sign and downward motion, except the radiative cooling becomes the dominant diabatic term and cancels with the subsidence warming. Observations do indicate that this approximation appears to be largely true in the tropics. However, another possible explanation for why equatorial waves propagate slower than the free solutions is that the propagation speed is a combination of the phase speeds of both the first and higher baroclinic modes. Indeed, diabatic heating, especially mature mesoscale convection that occurs in the upper branch of these waves, takes on a second baroclinic vertical structure that cannot be captured by the system of equations presented that assumes that all variables have a first baroclinic structure. The second baroclinic mode has a propagation speed of only 23 meters per second compared to a speed of 49 meters per second for the first baroclinic mode in an approximately 16 kilometer deep troposphere. This concept is related to the moisture stratiform instability, which is one way of describing the growth of equatorially coupled modes. Again, detailed explanation of this is saved for a more advanced discussion. For now, we'll settle with the notion that a complete understanding of mechanisms that explain equatorial wave propagation remains unobtained. The vertical structure of the equatorial waves is often tilted with height, and these tilts, can also help identify the waves. This and following plots are time-height diagrams, for which the zero time lag on the x-axis represents the time at which precipitation in the coupled wave is at its maximum at some location. We can see that this is a brightness temperature corresponding to OLR anomalies up here, and it's at a minimum at lag equals 0. A positive time lag represents the vertical wave structure above the same location at some time after the precipitation maximum occurs. We will first start by looking at the typical Kelvin wave vertical structure. Dark shading in all the fields represents positive anomalies. For an eastward propagating disturbance like a Kelvin wave, a negative time lag is experienced at a location east of the convective maximum. Therefore, the x-axis on these plots for eastward propagating disturbances is reversed with negative lags on the right. This way, the x-axis can also be thought of as a longitudinal axis from west on the left to east on the right. The zonal wind structure of the Kelvin wave therefore tilts westward with height. Convergence is seen at low levels. Here's a westerly anomaly and here's an easterly anomaly. And divergence is found aloft where convection occurs in this region. The convection is accompanied by a negative temperature anomaly in the lower troposphere and a positive temperature anomaly aloft. The specific humidity anomaly tilts westward with height as well. This means that moisture is at its largest concentration before the convective maximum in the wave occurs in the lower troposphere. The moisture is then transported upward via convection and is at its maximum in the upper troposphere around the time of the convective maximum and shortly thereafter, when decaying stratiform precipitation may be present. Thus, the convection in a Kelvin wave acts to transport MSC-rich air from the lower troposphere to the upper troposphere, making the atmosphere more stable when it is unstable, making it less stable when it is already stable. The Equatorial Rossby wave, whose vertical structure is shown here, also has a meridional wind structure. The anomalies plotted here are at an off-equatorial site around 7 degrees north. Note how the x-axis time lag is plotted for a westward propagating disturbance. Again, the left side of the plots represents west in space. Zonal and meridional wind anomalies tilt westward with height. The temperature anomaly shows a higher order baroclinic structure, and the humidity anomalies are generally in phase with the convection. The mixed Rossby gravity wave exhibits meridional winds that tilt eastward with height near 7 degrees north in the troposphere. In the stratosphere, they tilt westward with height. The vertical structure of the temperature is similar, with a second baroclinic structure in the troposphere present. Like the Kelvin wave, the humidity anomalies in the lower troposphere precede the convection, and the upper tropospheric humidity anomaly is nearly in phase with the convection. The much faster moving n=1 westward propagating inertia gravity wave near the equator has a vertical structure at the equator that looks like the off-equatorial mixed Rossby gravity wave structure that we just saw. There is the mixed Rossby gravity wave. Here's the n=1 westward propagating inertia gravity wave. The n=0 eastward propagating inertia gravity wave has a vertical structure at 7 north as shown. Lower troposphere, positive humidity and temperature anomalies again lead the convection, and a westward tilt with height is seen for both fields in the troposphere. Except that in the upper troposphere and stratosphere, the temperature anomaly begins to tilt eastward with height. Meridional and zonal wind anomalies generally tilt westward with height in the troposphere. All the waves discussed generally have very different spatiotemporal scales. For example, observed inertia gravity waves tend to have short wavelengths and propagate quickly. Equatorial Rossby, Kelvin, and n=0 waves typically have lower wave number and larger wavelength. The temporal scale of variability in disturbances that propagate slowly and with long wavelength tends to be shorter than that seen in inertia gravity waves. However, all the waves that possess at least some gravity wave characteristics share the same transition of convection from shallow clouds to deep cumulonimbi. In the suppressed phase of any of these waves, dry air subsides, creating an inversion that suppresses convection that itself is rooted in the boundary layer. As the upward branch of the wave approaches from either direction, the free troposphere becomes less statically stable and convection can grow. The convection deposits moisture into a sequentially deeper layer, allowing subsequent convection to grow even taller because the air it entrains is less dry than that entrained by the previous convection. Eventually, the atmosphere becomes unstable and moist enough to support deep convection. This is why we often see a buildup in moisture in these time series of vertical profiles that I just showed, such that the vertical structure of humidity anomalies tilts opposite the direction of motion of a wave with height. This paradigm of convective buildup in gravity wave disturbances, or those that contain gravity wave components, is applicable across a wide range of spatial and temporal scales in the tropics. Next, we'll apply it to an even slower moving convectively coupled wave disturbance, that associated with the Madden-Julian oscillation.